me start recording. All right, so welcome everyone to ECE 2 final review. You can interrupt any time to ask a question, and if you're not asking a question, if you could please mute your microphone. So today we have myself, Cody Fan, and Aaron Wissing leading this review session. So these are some of the topics that we will cover. Unfortunately, we didn't have time to prepare the Schottky diode, but I promise you that after this review session, I will record a separate video covering the Schottky diode. Yeah, so first things first, I'll just go a quick review of the Fermi-Dirac distribution. So let me see if I annotate. Interesting. But anyway, the Fermi-Dirac distribution it is a statistical distribution that basically tells you how likely it is for a specific particle, and in this case, an electron, to be at a specific energy level. And so, yeah, and then thermal equilibrium in a semiconductor. So basically, this is when the number of holes and electron carriers in the semiconductor material do not change over time. So it stays constant. How you change this is by doping. So you add so you add a material that can accept electrons, or you add a material that can or you add a material that can donate electrons. And these are the equations that govern it. And the derivations for these equations involve integrals with the Fermi-Dirac distribution. And it's in the Neiman book. And one thing that they assume is something called the Boltzmann approximation, in that the difference between the conduction band energy level and the Fermi level, and the difference between the Fermi level and the valence band level is greater than 3 times kT, where K is the Boltzmann constant and T is the temperature. So this is the freeze-out intrinsic and extrinsic regions. So the number of carriers in the intrinsic region is determined by thermal excitation, while in the extrinsic region is determined by doping. And in the freeze-out, the temperature gets so cold that there just aren't any carriers in the conduction band. And then intrinsic semiconductors. So basically, for an intrinsic semiconductor, the number of electrons is equal to the number of holes. And because of that, the Fermi level is right in between the conduction and, well, it's not quite right in between the conduction and valence band, because it's also dependent on the density of states of the conduction band and the valence band, but it's very close to it. And the equation here, that n naught times p naught is equal to ni squared, is a very important equation that, as you have seen in your class. Yeah, and then for extrinsic semiconductors, what you basically do is you add, let's say you have silicon, right? You add a group 3 element, and that group 3 element acts as an acceptor. So that's how you make a p-type semiconductor. And for n-type, you add a donor. So you add something from group 5. And the equation for n-type and p-type for the Fermi levels is determined by these two equations. As you can see, the intuition behind them is basically as you put, if you dope an electron, or not an electron, a semiconductor with a donor, the Fermi level will go closer to the valence band, because, or to not the valence band, to the conduction band, because more electrons will be excited up to the conduction band, thus raising the Fermi level. If you add acceptors, then there's going to be less electrons in the conduction band and more holes in the valence band, thus lowering the Fermi level, as you can see by these equations. So this is a question that you guys did at the end of last time. So just a quick refresher on doping in semiconductors. Although if there are any questions, please ask. Oh, I should probably give you guys some constants too. Let's see. I'm gonna type in the chat some constants that you guys need to solve this. And then if you are done solving, just type your answer in the, just PM me your answer, or you can just give a thumbs up or raise your hand. And if you want me to scroll back to the equations, just let me know. Okay, we'll give you guys another like 2 minutes or so. Also, if you need any equations, I can always go back. All right. So the answers are the following. So for A, it's 0.365 eV below intrinsic Fermi level. For B, it's 0.365 eV above intrinsic Fermi level. And for C and D, it's yeah, they are identical because NA and ND are identical. Yeah, yeah, so ND in part B is the same, or N naught in part B is the same thing as ND, and then P naught is the answer I show here, and then NA in part C is the same thing as PO in and uh, and and then NO is the same thing that I show here for C here. And you basically use the N naught P naught product to get that. The fact that N naught times P naught is equal to Ni squared. And then for A and B, what you do is you use the equations here to get the answer. So this is another question. So, and it's from last year's final for Chiwei Wang. The hints I will give you is to think about the Fermi-Dirac distribution and what the Fermi-Dirac distribution looks like for a p-type semiconductor. If you have an answer, I guess just raise your hand and yeah, feel free to unmute yourself and explain how you got there. Oops. If you have any questions about the terminology in this question, feel free to ask. I know when I was solving it, I had to look up what energy eigenvalue meant. And that's basically, it's basically energy. I don't know why he added the word eigenvalue there. Do you guys need more time or do you guys want to move on? Okay, I'm not getting much responses, so I don't know what's going on. Uh, but basically, the way you actually solve this is what you basically do is you want to recreate some type of graph like the one I show here. So as you see, you have the Fermi-Dirac distribution in blue, and then in green, you have the density of states of both the valence and the conduction band. And so we want to do it for p-type semiconductors. So what we do is we take the extrinsic p-type graph and we turn it by 90 degrees. So the Fermi Dirac is the distribution, and the density of states is the x-axis, and the energy is the y-axis. And then the Fermi level for the p-type will be closer to the valence band than the intrinsic, because there's less electrons in the conduction band, because they've become holes because of the acceptors. And yeah. So basically the solution, it should look something like this. So what's interesting is that this is also in the Neiman textbook. But yeah, and then what you would also draw too is you would draw holes on the valence band and a bunch of electrons on the valence band as well. And yeah. Before I move on, are there any questions? Okay. So let's move on. So compensated semiconductors. So if we have donors and acceptors in the same region, we have something that's called a compensated semiconductor. So all the problems that I've showed you before, I only gave you acceptors or donors. I never talked about them existing at the same time. But there's a set of equations called the quasi-neutrality equations that take advantage of the fact that the semiconductor is quasi-neutral, meaning that in equilibrium, a semiconductor has no net charge. So basically what that means is that uh, the amount of electron carriers at equilibrium plus the number um, of acceptors is equal to the number of holes plus the number of donors. And then you can do some math and you can get this equation over here. Um, and then the next thing is mobility and mean free path. So when we think about mobility, what it basically means is how well the electron is able to move through the material. Um, and this mobility can be, so the path of an electron can be impeded upon by two things. One is ionized impurity. So basically you have a bunch of junk in the material the electron's trying to move through that's kind of causing a traffic jam, right? It's like if you have a bunch of cars on the highway and you're trying to get to somewhere and you're like that one electron, right, in that car. If there's more like other cars around you, it's harder for you to get to where you want to go. For phonon lattice scattering, that's basically due to thermal motion of particles. So if you're trying to like run a straight path, right, and you have some crazy dude that's swerving left and right, I guess it makes it harder for you to get to where you want to go safely, right? That's kind of what phonon scattering is. Um, and so basically both are related to temperature. So the ionized impurity, one, um, it's related to temperature by a factor of T to the 3/2. So basically as temperature increases, the effect of the ionized impurity on mobility is made less. And this makes sense because if you're on the highway, right, and cars are moving like fast, right, then you can also get to where you want to go pretty fast. Um, and basically the T is like the speed of how fast these cars go, kind of. And then NL is basically the amount of cars on the street. So that's like the amount of donors plus the number of acceptors. And the more cars you have on the street, the more of a traffic jam you have, meaning that the mobility is less. And for phonon scattering, as temperature decreases, there's less vibrations, right? Um, so as the guy's like swerving around slower, right? Then the you'll be able to get to your uh, location faster. And someone asked, is there a link to the slides? Yes, there is. Let me send that to you real quick. The slides, these are the slides, if you want to take a look. Yeah, and then, okay, where was I? Oh, right. So basically to get the total mobility of the semiconductor, what you do is it's the same thing as a parallel resistor. So the total mobility is the inverse of 1 over the mobility from the lattice plus 1 over mobility from the phonons. Um, and dt over mean free path is, you can think of it as the probability of a scattering event occurring. And we can basically, to get the total probability of a scattering event occurring, So dt over t total, tau total is, we can just basically sum the probability from both the ionized impurity and the phonon events as a collision occurs due to the first effect or the second effect. And they're mutually exclusive. So if you have taken probability theory, if you have two disjoint events and you have their union, then you can add them, add the probability. So drift current. Whenever you hear drift current in ECE2, it refers to current due to applied electric field. And so we want to basically add the current due to the holes moving because of the electric field, plus the current due to the electrons moving due to the electric field to get the total drift current. And so this is just a list of helpful equations to get the drift current. So carrier mobility, how easy it is for the carrier is to move. So for holes, it's charge, fundamental charge times average scattering time over effective hole mass. And for electrons, just replace the hole mass with electron mass. And then carrier conductivity, you can calculate that based on mobility times fundamental charge times the number of the carriers there are. So that's basically how susceptible it is to current. And average drift velocity, that is mobility times electric field. And then total conductivity, just add the two, and total current density is you add you just take the conductivity, total conductivity times the electric field. And are there any questions? All right, I don't see any, so I will move on. For diffusion current, so there's two currents. There's drift current and there's diffusion current. For diffusion current, it's basically stuff moving from high to low concentration. So it's like osmosis, wind, going from high pressure to low pressure, right? And also you have electrons and holes in semiconductors. So basically there's a current caused by this effect, moving from high to low concentration. Because whenever you have a carrier electron or hole that moves, it creates a current. And so the total diffusion current is just the diffusion current due to the holes plus the diffusion current due to the electrons. And basically, because it's stuff moving from high to low concentration, you take the gradient. So for holes, the equation is the fundamental charge constant times another proportionality constant times the derivative of the carrier density, of the hole density. Basically, you want to move from high density to low density, and that's how you get your current. And yeah, and the total current is just the diffusion current plus a drift current. So the stuff caused by high to low concentration plus the stuff caused by electric field. Are there any questions? All right, yes, I should also explain the Einstein relation. That's basically, so this proportionality constant here, it's called the, I think it's called like the diffusion constant or something. So basically, if you take this constant and divide it by the mobility, you get kT over E, which is something called the thermal voltage. And it was discovered by Einstein, who, yeah, he's a smart man. Are there any questions about this? Okay, there do not appear to be any questions. Moving on. So did you guys cover Hall effect in lecture? Okay, I will skip Hall effect. So question time. So basically, anyone can just unmute themselves and answer this. How do you describe phonon and ionized impurity scattering, and how do they scale with temperature? This was also on Chiwei's final last year. And we also just went over this in our slides. So Anton direct messaged me and said that phonon scattering is about the lattice vibrations, and ionized scattering comes from the dopant's Coulomb interaction, and that is correct. So if you remember from one of the previous slides, I talked about how phonon scattering is from the vibrations of the random dopants or of whatever or the stuff that's in the semiconductor, right? And those are called lattice vibrations. And ionized scattering comes from a bunch of extra junk, right? Or dopants that are in the semiconductor. Um, and uh, and it really and it causes this like type of friction effect because of this Coulomb interaction. So each dopant produces its own electric field, and as a result, it causes this type of friction. Are there any questions? Okay. So how do they scale with temperature? So for phonon scattering, so as temperature decreases, the amount um, of lattice vibrations, so the amount that the stuff inside the semiconductor will vibrate, also drops. So therefore, the effect is minimized. Um, and so it has a factor, scales with a factor of t to the negative 3/2, right? Because as the temperature gets larger, or yeah, um, the mobility gets lowered. Um, and then for ionized scattering, so as the temperature increases, the carrier moving through the thing has like more thermal energy to move past the Coulomb interaction, if that makes sense. Are there any questions? Okay, moving on. So generation and recombination. So basically, electrons and holes are created in pairs. So they're created in pairs and they're destroyed in pairs. It's like if for every person here we also had an evil twin, and the moment we met, we also killed each other. That's kind of what's going on here. And so because the generation and recombination happens in pairs, the generation rate and the recombination rate for holes is equal to the rate for electrons as a result of this electron hole pair type duality. And also the amount of excess holes caused by generation is equal to the amount of excess electrons caused by generation. Because if everyone here had an evil twin, then well, there's 11 people here, then there'll also be 11 evil twins. So if there's 11 excess holes, there's also 11 excess electrons. Yeah, so case one, thermal equilibrium. Electrons and holes get excited at similar rates, and the amount of carriers stays constant, and so generation is equal to recombination. This is thermal equilibrium is when the N naught P naught product holds. So if you are not in thermal equilibrium, you cannot multiply N and P to get Ni squared. But if you have excess carriers, what you can do is you can separate out the excess carriers from the thermal equilibrium carriers, right? So you can have the total holes is equal to the equilibrium holes plus the excess generated holes. And for the and the same thing for the electrons. And basically, these carriers are generated by generating some external force at some rate. So you give the system a kick, basically, and in turn, the system produces new things because of that kick. Yeah, and what is low-level injection? So when excess carriers are much less than the equilibrium. So this is an assumption that is often made to simplify a lot of calculations, I guess. And yeah, are there any questions? Okay, moving on. So when we talk about the Fermi energy of a semiconductor, we can only really do it when we are in equilibrium. Why is this? Does anyone here want to take a stab at that? Okay, so basically, Fermi energy is only defined in equilibrium because when we have electron hole generation, go to the last slide. Oh, I forgot to explain this, but when you have excess carriers, the amount of carriers it changes. It's not constant with time anymore. So it obeys this differential equation that we have here. And so as a result, because it changes, we can't really define a Fermi level because it would just be changing all the time. But we can solve this by defining a fake Fermi energy level or a quasi Fermi energy level. And Basically what we do is we kind of just cheat, right? We just basically use the same equations we did before for the thermal equilibrium case, except we just replace the quasi, the actual Fermi level with like the quasi Fermi level, and we replace the holes in the equilibrium with the holes in equilibrium plus the excess carriers. Any questions? Oh yes. So Fermi level, you can only really define it in equilibrium, um, because if we're not in thermal equilibrium, if we're in case two, where we have excess carriers, where we're generating some external force at some rate, then what happens is that the amount of carriers, um, it changes. It changes with time, because there's some force or there's some generation rate there. Um, and it obeys this equation here. So dn over dt, dn by d, the derivative of n with respect to t, um, and is equal to a constant alpha r times ni squared minus nt pt. And I believe the same can be said about holes. So you just replace the n with the p. And I think there's something with like the signs changing somewhere, but yeah. Yes, Fermi energy is typically seen as a constant. Um, it's normally constant with respect to time. Fermi energy, what it is, it basically, um, it kind of, it's a heuristic that kind of tells you uh, like where most of the carriers are. So like if most, so like if most of the carriers are holes in the valence band, um, because we have acceptors, then the Fermi level will go lower, right? Um, and if we have like electrons in the conduction band from adding a donor, then the Fermi energy will be like higher than the intrinsic, right? Um, and this is constant with respect to time, right? Because in that case, we're talking about thermal equilibrium. Um, so like Fermi energy, it depends on the number of dopants that we add in, and it depends on the material. And it does not depend on time. And so when we have something that depends on time, we can no longer define a true Fermi energy level. Does that answer your question? All right, very good. Um, so this is another question from Chiwei Wang's last year's final. So I have given you some constants. You need to solve this. Basically, this is a plug and chug. So I will give you about, let's say, 4 minutes to solve this. And just like type your answer in the chat when you're done. Yep, the answer in the chat is correct. So how to solve it? So you use the NP product to get N naught at equilibrium. So we know that because we have acceptors, we can set our P at thermal equilibrium as NA. And then we can do some math to get N naught at equilibrium. And then we plug all the constants in into the Fermi quasi-Fermi level equation, and we do the math, and we get an answer. If you guys see this question on your final exam, please get it correct. It's a free 12 points. Yeah. All right, so Aaron will be doing the part on the PN junction.
Hey guys, so I'm going to be talking about PN junctions. First of all, I guess I'll just start off by saying what is it? Well, you take two slabs of semiconductor and you join them together. And the key thing is that they have different doping levels. So the P side, of course, has a P doping with acceptors, and the N side has N doping. You can sometimes have one-sided junctions where one has a heavier doping, and then the amount of depletion width you have will be different. So yeah, you'll basically find out that with heavier doping, you actually get a smaller depletion width. So like on the N side, in this picture, the N side has heavier doping. Yeah, and so when you join them together, basically there's diffusion that occurs along that boundary because you have a gradient. There's a high concentration of holes, for example, on the P side and not so much on the N side. So they're going to diffuse across. And but eventually, once they diffuse, they'll be recombined in the other section. And what they leave behind is these ionized donors. So, for example, all the minuses are like Na minus, and all the pluses are Nd plus from the donors. Oh, and by the way, this is kind of an aside, but if you ever get confused about like acceptor versus donor, one way to remember like where the Na goes, the Na goes with a P, and I think of this because like acceptor has a P in it, and then donor, like the word donor has an N in it. So yeah, that might help you keep the two straight if you just want something really rote. But yeah, so anyways, that's neither here nor there. Just to help you remember. Anyway, so yeah, you get these ionized dopants left behind, ionized donors, sorry. And what that causes is kind of like a dipole that they cause an electric field, a very strong electric field. You can draw the field lines, as you know from something like 101A or even just like physics 1C. If you have a positive point charge, it has electric field lines emanating out of it. It's kind of similar here. So yeah, the field's going to go from positive to negative, and basically sweep up any carriers across the junction.
Oh, sorry,
Okay.
I missed
Yeah.
it.
So basically, other than that, yeah, so drift dominates in the middle of the junction, and then diffusion will allow those carriers to diffuse and then be swept up when you start applying biases. Yeah, okay, so here are two equations that are pretty key with the PN junctions. One of these is the built-in voltage in terms of the doping levels. So if you know the doping, you can figure out what VBI is. And then here is how you can also calculate the depletion width if you know basically about the doping. And to give you a feel for how large the depletion widths usually are, like in a practical device, usually it's something around like a micron or even a little bit less, like third of a micron. Of course, that can vary a bit, but you know it's pretty small because we're looking at semiconductors. Okay, so I guess going on to the next slide, now that we kind of know how the PN junction works qualitatively, let's kind of put a quantitative aspect to this. And so basically this is one of the problems that I feel is like the most canonical. So for example, it might be a little bit easy for tests because you can basically find this derivation in a book, but the principles can definitely be applied to other problems. For example, if you have a graded junction, you would follow all the same steps that you, well, almost all the same steps that you do in this problem, which is basically using Poisson's equation. It's just going to be like a little bit more math intensive, but if you understand how to do this, then you'll be fine for those. So yeah, I think the way I'm going to do this is take note of what the question is, and then I'm going to share my screen and start solving it. Oh yeah, Cody, can you make my other user the host, co-host?
Yeah. Can do that real quick. There we go. Done.
Okay. Yeah, so we have a YouTube channel where I think we'll probably post the recording, right, Cody?
Mm-hmm. Yep.
Okay.
Let's see. Let me send the link of the channel.
Mm-hmm. Okay, so we have our PN junction. It's a slab like this, P side, N side. And so what I've drawn over here is the charge diagram for a PN junction. You can basically assume that all the charges remaining are inside the depletion region, and everywhere else is charge neutral. So that means that positives and negatives, in terms of charge carriers, they'll perfectly balance each other out, but not over here in this depletion region. Okay, and so one thing that you should assume is that the overall depletion region is charge neutral. I mean, it's basically like conservation of charge. It's just like, yeah, so from the outside is charge neutral, which means your END is, so that's like the amount of charge per length. And then these boundaries are, this one I'll call X and naught. So this is the N side. The other side's P side. And this boundary I'm going to call negative XP naught. So END times X and naught is the area under this diagram. And so then we have on the other side, XP naught times ENA minus. Okay. And then, yeah, you can cancel the unit of charge. And so basically you get charge neutrality. This will be useful at a later step. So you definitely want to know ND X and O is XP O and A. So basically, also what these variables mean, like this is like the length of the depletion region on the N side, that's XNO. XPO is the length of the depletion region on the P side. And so if this is a constant product, you can see how if I increase the A doping, like the Na, XP naught is going to go down. Okay, so knowing that, what the problem was asking you to do is do basically diagrams for charge, E field, and applied, or sorry, built-in voltage. Yeah, so we already did charge. You can kind of take that as a given, I guess. But then E field, what you're going to do is use like Gauss's law for charges. So what that basically says is the electric field changes based on where you are, and it's related to the charge. And so by one more step, what you're basically going to do is integrate that charge density to get the E field. Okay. So if you want to like derive all the exact expressions for this, you'll have to kind of like break it up based on the regions, like piecewise. So first I'll do for this region, which is the P side. You're going to have this. So x on the upper limit is just like arbitrary. And then on the bottom, it's xp naught. And it's going to be 0 everywhere else, just so you know. Yeah. Actually, one more comment is to get the E field. I'm going to change colors here. You can actually like not even do this with equations. It might be better to think of it more qualitatively. So you have a constant charge across there, and then if you integrate that, you basically get a line. Of course, the charge is negative, so it goes down. It's going to peak at 0. And then it's going to go back up with a slope that depends on what your END is. But because of the charge neutrality condition, it will end up back at 0 E field when you go back. Okay, so back to actually like working with the expression. So here you're just putting in your charge, which is minus CNA over epsilon. So yeah, quite simply, you get that. And you can figure out how to apply the boundary conditions and get the expressions for the other regions. Since for this problem, all you really want to know is like what's the value at that 0 point. I'm going to plug in E of x equals 0, and for that you get this value. So yeah, the magnitude of the E field. Yeah, okay, so moving on, now we want to get the voltage. And to get voltage, generally speaking, use this trick. Basically, like there's a derivative relationship. Yeah, so it's this. And then you're going to integrate. So I'm going to do what I did earlier and kind of just plot it qualitatively. And so that should be okay. So you start at xp naught. You basically have nothing. And then here you kind of have like you're integrating a straight line. So you get like a quadratic equation. But also notice the negative sign with this relation. This is Poisson's equation, or a form of it. So you get voltage going up like this. And then over here, there's another sign flip, but it's still quadratic. And there's like boundary conditions, so it's continuous. You get like this. And then the way that our built-in voltage is going to be defined is like this. You V naught or like VBI, it's same. So yeah, if you just want V naught, then you can make the bounds xn naught to negative xp naught. And then for this case, we just want the built-in voltage, not like the expression. If you want the expression, you just do the math. But here we can use a nice trick. So basically, we're integrating all of this triangle. So what we're going to do is we're going to use 1/2 base times height, because it's effectively the same as integrating. And so that's going to be this 1/2 E naught. So that's like over here. the value found over there. And then it's going to be times this effectively, xp naught plus xn naught. But just so you know, the depletion width is defined as this portion that I just wrote. So that's W, xp naught plus xn naught. And then for the E naught, you're gonna plug that in as well. Okay, so now one last point is, we kind of have a variable mismatch with the xp naught and the W, so this is where you're going to use the charge neutrality condition. So we found that earlier to be this. And then using the W is xp naught plus xn naught, you can basically get it down to one equation with two variables. So I'll do it like this, xp naught plus sub this one in. This tells you that W is xp naught. Then you can prefer to eliminate xp naught. Okay. So then you're gonna take this expression and sub into there. So yeah, to clean up this expression, I just like times ND and times ND on both sides. Yeah, I just like group these together because it reminds me kind of like parallel resistors, so it's pretty useful. Okay, so basically you can see that this is how you derive these equations. I think I had like a sign error around here, so maybe check that. I think we'll post a more accurate solution, but probably with less steps, so you'll have to fill it in on your own, but it'll have like the correct answers. Anyways, back to here. This should be right. And it shows that there's a square root relationship if you solve for W in terms of V naught. So basically everything would flip if you go for W. And you also have your built-in voltage.
Interesting.
With oh, Cody's back.
Sorry.
Sorry.
Internet
All
issues.
right. Yeah. Sorry. I'm going to stop my recording and let you finish it up so you can just merge the two.
Yep.
Okay. So yeah. So what I was saying here is basically this is approximately 1 over NA if ND is much bigger. So the smaller one is kind of limiting you. And so yeah, it's an approximation that kind of helps you if you want to like put some actual numbers to it. Yeah. Okay. So I think probably go to the next topic in a second.
Right.
Yeah, so I'm going to talk about the current in PN junction. Yeah, so I like the previous problem because I feel like it explains a lot of things in PN junctions pretty well. For the current, I didn't prepare as many problems, so maybe read up on that. But it mostly uses things that Cody talked about. So for example, if we plot this, it's basically the minority carrier concentration current that's going to determine how much current there is. And the reason for that is with the majority carriers, basically the two majority currents are balanced. And of course, this assumes that you're putting applied bias. Actually, yeah, let me discuss a few cases for the PN junction that you should know. Okay, so we have our P and our N. And now you want to hook up a voltage source to this. And so we're going to talk about what happens. So first assume that you have forward bias. So maybe before your depletion region looked like this. So now this will allow more carriers to start crossing the junction, and the depletion region is going to decrease. So some of these charge carriers are going to come and cover the donors and the ionized impurities. Yeah, and then when we think about the voltage graph that looks like this, so before we had something like that, now with the forward bias, basically this barrier has been lowered. So instead of just VBI, you'll now have like VBI and then the applied voltage lowering it. So that barrier has gotten smaller. Depletion width has also gone down. Now, on the other hand, if you have, say, reverse bias, so that means that, okay, in forward bias, you hook up the positive side to the P. You can remember that. And then reverse bias, you have the opposite going on. So in reverse bias, this barrier is now, it gets even bigger. So yeah, you have something like VBI plus V reverse.
Yeah, a good trick to remember forward bias is that P is for positive and N is for negative. And
Yeah.
forward is like that, and then reverse is the reverse of that. So
Then by a similar token, the depletion width is going to get bigger. So those are some good things to keep in mind with the PN junctions. Yeah, so just want to make sure I hit on that. You can look up the equations with like applied bias and plug the stuff in. It will also make sense. Okay. So yeah, basically like Cody was saying, when you have excess carriers due to an applied voltage, you can talk about them like this. These are minority concentrations. And they're the main source of current in your p-n junction. So yeah, this is like basically your J. And yeah, if you add the two together, you can write an equivalent expression that's basically like this, JS, where this is a bunch of constants, depending on this stuff. And so you have an exponential dependence on how much applied voltage you have. So if you plot an IV curve for, well, an ideal diode, what you're going to get is something that looks like this. Yeah, sorry, it's kind of hard to draw. Yeah, it's like a hockey stick. So that JS value is this, basically like reverse current density. In like analog electronics, if you're talking about currents, this will be called IS. Okay, so yeah, on the x-axis, what we have is the voltage, sorry, applied voltage. And up here, we have J or I. So yeah, basically the more voltage you apply, the more crazy this curve gets. And in a real diode, you're going to have like basically some like series resistance effects and other like things that are basically non-idealities. And I mean, really, your diode's going to blow up. So yeah, just keep that in mind. And then here you have like a breakdown voltage where the current's also going to increase a ton because the materials are basically like breaking down. So in real life, that usually destroys your diode, except for a couple cases like the avalanche diode and the Zener diode can be used and like operated close to this value and actually like exploit some of the effects. Okay, so yeah, last thing I just want to say is this type of form you have here, where it's like a constant times exponential minus one. It's actually like really useful to remember in like later courses as well. And so one trick you can use to remember it is say you have 0 applied voltage. You can see that it's going to be x of 0 minus 1. So you're right here. If you have VA being very high, you can totally neglect the 1. And that's actually kind of useful in electronics as well. If you have VA being like a very small number, or a very small negative number, then the exponent is going to be like something like completely tiny. And so you'll just have a minus 1 left over and you'll get minus JS. So that's how you can remember that that's this value. Yeah, so that's the IV curve. Know the ideal curve as well as some of the things that cause it to deviate from that. Yeah, and so the last point I wanted to hit, I guess, is besides studying all the current equations, also there's a couple like breakdown mechanisms that I touched on earlier. So one's the Zener diode. Basically, the reverse bias voltage gets so large, it creates an E field that's so large that electrons start tunneling between the bands. And so you get a very big current. So yeah, tunneling's definitely something that's kind of exotic, but this is one case where it gets useful. Another one is avalanche breakdown. So in avalanche breakdown, you have electrons, or I guess sometimes holes, but electrons move faster. So electrons that get accelerated so quickly inside the drift layer that they can actually knock other electrons out of the lattice, and then that will cause a chain reaction where each electron will knock another one, and eventually there will be a ton of collisions and just like a ton of current that will basically probably break down your device, but it can also be used to your advantage by making like an avalanche diode. Okay, so yeah, that's pretty much it. Do you have anything else to add about PN junctions, Cody? Because to be honest, I didn't really get a chance to cover everything, but hopefully showed you a few things that will be helpful.
I guess there's also like some generation recombination effects,
Mhm.
but I didn't prepare anything specific for that. So yeah, I guess you guys will have to read up on it. And
Yeah,
then there's
obviously, a review session isn't totally comprehensive,
yeah,
but hopefully it's a good start for your studying.
yeah, and then there's Schottky diode. You guys also have to review that on your own. I'll see if I can find the time to maybe make something about it, but it'll probably be hard for me. So yeah.
All right, yeah, so thank you guys for coming. We'll stick around a bit if you have more questions.
Oh, and also, yes, there's also junction capacitance. That's also
Oh,
can be
yeah.
interesting, and the small signal model that you guys should probably read up on. I guess what the small signal model entails is like a bias voltage and then like a small sinusoidal signal. Um, yeah.
Yeah, and you can linearize it with a Taylor series, and it basically lets you model things that are nonlinear in a way that's very familiar, like just with like resistors and capacitors. Um, yeah, so basically you have a circuit model that you can look up um, and yeah, have on your cheat sheet or something.
Maya, do you have any questions or? All right. Cool. Guess we can
I'm
start
good.
the.
I didn't realize everyone left too. Thank you.
Yeah.
When would you post it to the YouTube channel? Because like
Um,
you guys solve the example questions or just talk about them?
oh, the example questions. So some of the solution I did put in the slides. Some of them like they were talked about before in like the slides. So I didn't
Okay,
feel the need to, yeah.
cool. Awesome. Thank you so much.
Yep. Well, guess that's it.